Buenos días con todos. Hoy día estamos reunidos aquí para participar en el seminario organizado por el Instituto de Investigación Científica de la Universidad de Lima, junto a la carrera de Ingeniería Civil, como parte de las actividades del grupo de investigación que afiere al instituto. El título forma parte de la investigación que viene desarrollando el profesor investigador Emilio Barchiesi de la Escuela Nacional de Ingenierías de Brest, en Francia, y del Centro Internacional de Matemática y Modelos Complejos de la Universidad de L'Aquila. Deseo introducir a la directora del instituto, la profesora María Teresa Quirós. Adelante, por favor.
Muy buenas tardes, bienvenido, doctor Emilio Barchiesi, a este espacio virtual que nos permite estar conectados desde lugares que no son del Perú, ¿no? Sino que son lejanos, pero que nos permite conversar sobre temas tan importantes. Gracias al trabajo del doctor Francisco León, quien lo conoce y quien ha organizado esta reunión, podemos tener la suerte el día de hoy de tenerlo conectado con nosotros para discutir un tema que no es simple, que es complejo, pero que atañe no solo a países, digamos, europeos, sino también a países latinoamericanos como el nuestro. Sabemos que la actual investigación que usted dirige está orientada a lo que se llama, a un tema complejo también, la modelización computacional de los fenómenos del daño, incluyendo la propagación de grietas frágiles y dúctiles en materiales metálicos y cementosos. ¿Cierto? Usted está siendo traducido sobre esto. El objetivo final, entendemos, de esta investigación, doctor, es el ahorro sustancial de materiales, transporte y costos de inversión de capital en que la tecnología transfiere, combinando con la investigación y el desarrollo que pueden ayudar a alcanzar la reducción de factores de incertidumbre que se relacionan al diseño estructural. Este tema, como señalo, que es un tema importante, complejo en el área de la ingeniería civil, tiene para nosotros una gran trascendencia en un país como el Perú, complejo también, ¿no? Donde tenemos condiciones, digamos, condiciones que se ajustan directamente a estos planteamientos que usted está señalando y que viene investigando. De modo que yo le doy las gracias por poder dialogar con estas personas. Tenemos más de 100 participantes interesados en lo que usted pueda decirnos. También quisiera resaltar que este evento, digamos, esta reunión, es parte del esfuerzo de nuestra universidad, de la Universidad de Lima, de la Facultad de Ingeniería Civil y de nuestros investigadores agrupados en un grupo de investigación para internacionalizar nuestra universidad e internacionalizar la investigación y poder a través de este diálogo compartido sacar enseñanzas que se apliquen también a un país como el Perú. Por esa razón es que le doy de verdad la bienvenida, felicito este vínculo entre Francisco y usted, Emilio, y espero que podamos continuar colaborando en materia científica y de producción de conocimientos en los próximos años y meses y de la manera más activa posible. Muchas gracias, doctor Barchiesi, y los dejo, Francisco, para que puedan continuar.
Muchas gracias, profesora María Teresa. Como lo ha también recordado la profesora, Emilio Barchiesi forma parte del grupo de investigación de métodos numéricos computacionales, computación gráfica y científica del IDIC, siendo él un colaborador. Precisamente se está realizando un proyecto de investigación con él en el presente año, con financiamiento del IDIC. El proyecto versa sobre la modelización matemática y numérica de la fractura, evaluación de las recientes teorías de campo de fase y aplicación a materiales microestructurados innovadores. Nuestro deseo es que a raíz de esta presentación que va a realizar Emilio, también podamos involucrar a nuestros alumnos y colaboradores, porque el tema es bastante amplio y relacionado con, como lo ha mencionado la profesora, la parte de innovación tecnológica, ¿no? Entonces, es un tema que, si bien es cierto, en Perú todavía no se está tratando mucho, ¿no? Es un tema que tiene un ámbito de investigación con diversas colaboraciones por parte de Emilio, con investigadores de Estados Unidos, Francia, Alemania, Rusia. Y bueno, muchísimas gracias por vuestra presencia a todos. Adelante, Emilio. Prego. Solo para recordar, la exposición de Emilio se va a realizar en inglés. En la parte inferior de los comandos de Zoom hay una ventanita de interpretación que puede hacer la traducción simultánea. Precisamente ustedes pueden escoger ahí si desean escucharlo en inglés o en español.
Great. So at first, let me say that I'm really honored of having been invited here to give this, say, distance talk to you, in front of all the students of your school. And I would really like to thank all the organizers, because I must say that behind all this, there is really a lot of effort. And then I would like to thank the management of the university, and in particular the Dr. Kiros, who is the director of the scientific investigation group of University of Lima. And I would like to thank Professor Trujillo. I think that this collaboration will last for a very long time, and this talk is directed to all those people who are currently studying engineering and are curious to know what are the current challenges in damage mechanics and how, say, addressing these challenges might be beneficial for all our countries. So now we'll share my screen so you will see my presentation. So I think that all of you should see my presentation right now. So let me just say a few words about myself, adding to what has already been said by Professor Francisco Trujillo and Dr. Kiros. So my name is Emilio Barchiesi. I am currently research fellow at the École Nationale d'Ingénieurs de Brest in France. And I'm research fellow also at the International Research Center for the Mathematics and Mechanics of Complex Systems. And in these last months, I have been collaborating with the Instituto de Investigación Científica de la Universidad de Lima. I'm part of a group which is working on an investigation project which is exactly devoted to the study of fracture mechanics and, more broadly speaking, damage mechanics. So here in this talk, I will try to give you a taste of what is current research in damage mechanics. So for sure, all of you have seen the very sad fall of a building in Miami some 2 weeks ago. So actually, if you look at the BBC website, you can see that at a certain point, when they talk about this very sad event, they mention that structural engineers would look at design plans, so how the building was constructed, to know exactly how the building was, say, assumed to be in properly working conditions. And then what they say is that they will see how the building was constructed, which is if really these plans were followed in the realization of the building. Take samples of steel and concrete, which is try to make some material characterization, including look at signs of corrosion. Then they would look at foundations and understand if any unusual thing took place before the collapse. And why do they need all this information? They need all this information because once they have the information, they can simulate different scenarios and pinpoint how the collapse took place. So there is a very important word here that I found on this web page, which is simulate. So actually, in current engineering, simulation, which is the computation of a given mathematical model to compute some predictions that then should be compared with reality, with measurements, is at the basis of current engineering. So here, simulation is the keyword also for our work, because in our work, in our everyday work, we try to predict how damage will evolve using both theoretical, which is modeling, and computational, which means simulation tools. So I think that it's not necessary to try to explain and motivate why we should study damage mechanics, but just to be on the safe side, please remark that just in 2021, so just in less than 7 months, we had more than 8 collapses, but major collapses that happened in the world. The last of which just happened a few days ago in India. So damage mechanics can help us to save not just only lives, but also it can help us in improving our quality of life and the costs which are related to the maintenance of buildings so that they can be always safe for all of us. So as you see, damage can take many forms. Here we have just a few of them. So one form is the collapse of bridges. So you can see that here on the bottom left, we have a picture of the bridge over the Polcevera in Italy, in Genova. This was a very big collapse that unfortunately caused the death of more than 40 people. Then we have collapse of airplanes, or in general, some transportation system. We have the collapse of buildings, of masonry in particular, who are quite susceptible to damage, and so on and so forth. So you have seen that these topics have a very close connection with our reality. But then, is this topic connected in some way to future short-term potentialities in Peru? Well, the answer is yes, because just recently, the government of Peru launched a national infrastructure plan who granted 104 billion for the next 20 years to bridge, the Peru's long-term infrastructure gap. What is the main scope and the main challenge that has been launched by the government. The government intends to create a database of BIM models, which is building information modeling, that can collect all the data about a given building. And the challenge that we, as modelers, should undertake is how to connect all this huge bunch of information that will be available for each building through this BIM system with modeling, so that very accurate conditions can be done on the building to ensure its safety and its efficiency in terms of structural and energetic performances. So actually here, let me stress the fact that what is really important is that when you have a model, its accuracy is proportional to the accuracy of the information that you have about the problem you're dealing with. So having a building information modeling system which is capable of giving really accurate and extensive information about a building can really help in making, say, reliable predictions. So this is why I think that what we are doing right now, which has already been started in Europe and also a part of the US, will be very relevant for the near future. So in our work on damage, we have to face some everyday challenges, as I mentioned. One of the main challenges is that damage occurs through a very wide range of mechanisms, because you have cementitious materials, look at concrete, ceramics. It happens in fibrous materials that can be either artificial, natural, biological tissues, but can happen in fibrous materials that are part of composite materials, can happen in metallic materials like iron, steel, aluminum. So, and all of these materials are connected with different applications, which means with different boundary conditions, with different problems related to the environment. So say that for cementitious materials, you deal mainly with buildings. Then if we talk about fibrous materials, you deal mainly with high performance transportation systems, because composites are widely used in cars, are widely used in airplanes. While if we deal with metallic materials, very often we deal with large infrastructure, like bridges, for example. So the first challenge is related to this wide range of damage mechanisms that should be studied. Of course, there does not exist a single model which is able to deal with all of these at once. So ad hoc solutions should be developed for each of these problems. And in undertaking this challenge, we have mainly two choices on the modeling side. We could use either discrete approaches or continuum damage approaches. So of course, discrete approaches are approaches where the modeling uses a finite number of degrees of freedom, while in continuum modeling, we have an infinite number of degrees of freedom. In turn, the continuum damage approach divides into two other sub-approaches. One is the macromechanical, which is actually, I don't care about the nature of the system, I just give a phenomenological macro-scale law of describing how it is behaving. Then there is another approach, which is the micromechanical approach, which seeks to create a connection between the micro-scale, so the microstructure of the material, be it grain, let's say grain-grain interactions happening in concrete or in iron, or fiber-fiber interaction occurring in fibrous materials, and seeks to connect all these phenomena with a continuum description at macro scale. Of course, each of these descriptions has its own pros and cons. So, of course, discrete approaches usually need a very high number of degrees of freedom because they are by nature very refined in describing the nature of the material under study. Discrete approaches are very often used in atomic models, which are, of course, too refined and so too computationally burdening to be really used in applications. They are seldom used in mesoscale models, which are discrete particle models, which kind of coarse grain the atomic models. And finally, the most computationally feasible models are the continuum ones. But this, of course, comes at a cost. The cost is that these models can, encode less information in the constitutive modeling with respect to discrete approaches, which are more refined. So one should find a trade-off. And as you see, this trade-off is found when you actually apply the micromechanical approach. So you try to connect the micro scale with the macro scale. And in doing so, we utilize a constitutive modeling at micro scale, which is a kind of specification of equivalent spring elements acting, or at least mediating, the interaction between two adjacent grains. So we'll see that for cementitious materials. Of course, before going into complex things, we'll say complex geometries, complex material laws, complex damage laws, and loading conditions. We'll just focus on a very simple case, which is the case of a softening spring. So at first, I will briefly introduce the mathematical formulation. We'll deal with a single degrees of freedom system with damage. Then we specialize this formulation to a simple damaging hook spring. Then we'll see analytical solutions for such a case. I'll go very briefly through some numerical methods that can be used to address this very simple system so that you get a taste of what it looks like doing research in computational mechanics when we deal with discrete systems. Of course, very simple ones, but we work in real life with very complex systems. And then you'll get a taste of how applications look like. We'll speak about grain-grain interactions, how these interactions can be used to have a discrete modeling of a masonry structure, including the fracture, of course, behavior. Then we'll go through how we deal with brittle fracture using continuous models, and at the end, the more complex model you would be dealing with should you work with us, which is a model derived by homogenization of an elastoplastic damage granular material. So let me just say something in advance. Every time I will say explicit, I will mean that if we are in an iterative process, we go from step I to step I+1 just by a closed form expression, so without doing any further iteration. While if I say implicit, that would mean that we go from step I to step I+1 through a series of steps. So there will be no closed form expression to go from one step to the other. Well, so let me come to the formulation. So let us consider that time is continuous, which means that time continuously increases from 0 to the time horizon. We have a finite dimensional system having just 2 degrees of freedom. 1 degree of freedom is, say, u, which is, you can think of it as a displacement. And the other one is the damage, which is simply denoted as d. So this d is a kind of parameter which is not only expressing, say, the extent to which damage is affecting a material, or in this case, just a system, because this is a global parameter. But it also gives, say, it's a way to encode the irreversibility of this damaging process. And how is it encoding this damage irreversibility? Well, through a condition. This condition reads as damage can only increase in time. So whenever we look for a damage trajectory, which is for a law of evolution of damage, we look for an evolution of damage such that damage is only increasing in time. Mathematically speaking, this means that the admissible variations of damage with respect to an equilibrium state are positive, because, as I told you, the variation of damage in time can only be positive. Then we equip this system with an energy. As we work in a Lagrangian framework, so we use Lagrangian mechanics, we define a total energy functional for our system. So the total energy functional reads as the sum between the deformation energy of the system and the dissipated energy. Then we subtract here, to these energies, we subtract the energy which is entered from the outside, so the external energy, which is nothing but the work done by external forces which are acting on our finite dimensional system. Note that throughout this presentation, I will neglect inertial forces for simplicity. So then let me define what is the first variation of this energy functional. So the variation of the total energy is nothing but how the energy is changing from a given state, UD, if I perturb a little bit. Actually, I perturb of a very infinitely small quantity the energy. So I take a state U, D. I perturb it a little bit with admissible variations, and I go to see how the total energy is affected by this change. Then I perform the limit for this perturbation, well, the amplitude of this perturbation, to go to 0, so that we consider this first variation of the energy as nothing but the variation of the total energy for admissible variations of the kinematical descriptors, which are U and D, having arbitrarily small amplitude. Well, at this point, we can introduce, I think, the most mathematical thing you will see through this presentation, which is the maximum energy release rate principle, which states nothing but the release of energy, which is actually occurring at any time instant of the evolution of the system, is the greatest possible among all the admissible trajectories. So this is just a principle. We accept it as it is. Actually, this principle was formulated in 1948 by Hill in a very famous paper. And all our tractation is framed into this variational principle. And here we just discretize in time the formulation, which is we define time discrete equivalent quantities. Well, time discrete quantities equivalent to those which I have introduced before. So time just gets discretized into many intervals so that we can use algorithms to solve the problem. Well, the problem is find U and D such that they verify for each time instant this maximum energy release rate principle, which is here. Well, now we specialize our tractation to a very specific simple case, which is the case of a a classical spring, which is linearly damaging. So we choose as elastic energy just the square of the displacement of the tip of the spring, which is the displacement of this point here, while this point here is fixed. Then this is multiplied by an undamaged stiffness, KEL, and then this stiffness is in turn multiplied by what we call customarily in damage mechanics the stiffness degradation function. So if this is damage, when this is 0, then the rigidity, the stiffness of this system is exactly KEL. While when D increases, then KEL decreases until eventually it goes to 0. And so the spring will not be capable anymore of bearing any load and will reach what we call complete failure. Then we have the dissipated energy. So this is all the energy which is actually entered into the system as elastic energy, which after damage occurs is transformed into other forms of energy. So basically, this is the energy that, say, is transferred from the elastic one. Well, you know, you input from the outside some external energy under the form of external work, and then if damage is not occurring, then all this energy is transformed and is stored actually into elastic energy. While if some damage is occurring, then a part of this energy is stored as elastic energy, while the remaining part is stored as dissipated energy. Well, so if we compute the first variation of the total energy functional, and we compute also the rate of variation of the energy functional, and then we apply the previous principle without skipping all the computations, which are not relevant at this stage, we get two conditions. One condition is the usual equilibrium condition, which says that either displacement is kinematically fixed, in that case, we know what is the displacement because we fixed it, and in that case, this would be 0, so that this equation would be identically satisfied. Or if delta U is not 0, which means that we didn't enforce the displacement on the right tip of the spring, then this factor here would be 0. It will vanish. So what would we get is just Hooke's law with this damage correction, which is quite easy at this stage. Then we would get an unusual condition, which is called KKT, so Karush-Kuhn-Tucker condition, which basically states that the product between this factor here and the rate of damage should be 0. So, well, this equality is always fulfilled if d dot is equal to 0, which means if damage is not evolving, then this is automatically satisfied. But what if damage is not constant in time? So what if damaging is evolving? Then if damaging is evolving, this should be fulfilled. This equal to 0 should be fulfilled. Well, but you might argue that it's not given that solving this equation will give an increasing in time damage. Well, that's true. Indeed, if equating this factor to 0, you get that damaging is indeed decreasing with respect to the previous time step, then actually damage is not evolving because we know that damage can only increase. And so d dot equal to 0 is entering into play. Well, so now if you enforce displacement on the right tip, and we call this displacement control, it means that this equation here is automatically fulfilled, because delta U is 0. And then you just have to solve this factor equal to 0 for the damage variable. Well, this is just, this is straightforward, because you just get that D is equal to this guy here, which is the elastic energy without the damage correction, minus KT, which is a kind of threshold parameter, which is controlling the damage yielding, so the onset of damage, divided by KD, which is nothing but a kind of resistance to damage. The greater KD, this lower damage occurs. The lower KD, the quicker damage evolves. So, well, we enforce displacement using this law, actually. So alpha is a positive parameter, t is time, so displacement is increased. So if we know displacement, we can automatically compute the force through Castigliano's theorem. So here we load the structure, increasing the displacement. Force is linearly increasing until a threshold, which is controlled by this parameter here, KT. And then softening occurs. So we have here the onset of damage. Softening occurs until you get a stationary point for the force with respect to time. And then the force is decreasing until collapse. If we look at damage evolution, then what we see is that damage is not evolving until t is equal to 1, so until we get to this threshold here, and then damage increases until failure, which means damage equal to 1. So here, as I mentioned at the beginning, we have some algorithms to solve this kind of problems. Well, this problem is very easy. We have an analytical solution, but I'm going to show you some methodologies to solve this problem, this simple problem, not because you should really apply these methodologies for solving this problem, but because understanding how these methodologies work is much easier if you consider such a simple case. So in an explicit scheme, so when you don't need any further iteration to pass from solution at step I to solution at step I plus 1, where I is just a discrete time. So you have two displacements, one displacement applied at time I and one displacement applied at time I plus 1. What you do is just that. So at first you solve, so you know the displacement because we are in displacement control, and as you know the displacement, you can just solve for the damage, this factor here equal to 0, right? You get damage, and then once you have got damage, you plug damage and displacement here to compute the force. As easy as that. So if you have force control, which means you control the force, so you apply a force on the right end of the spring, you apply an extensional force, so a force which is pointing toward the right, then you can still find analytical solutions, but still these analytical solutions will be a bit more complex. Why? Because if you solve this time here the damage for the displacement, well, you get damage as a function of the displacement. But remember that here, displacement is not fixed. So you have still to solve for displacement. So you plug the damage that you have found here as a function of the displacement into here. So into here, you plug it here. And you get a third order algebraic equation for the displacement when the force has been fixed. Well, of course, a polynomial equation of third order admits three solutions, and not all these solutions might be admissible or even real. So in fact, you get three solutions. So here you have the displacement versus time plot for each of these solutions, which are in green, yellow, and blue. Then you have the damage versus time for these three solutions. So as you can see, the blue solution is unfeasible because damage is greater than 1, which is impossible. Then when time increases, the green one is a good one because damage is increasing. Then if faults must increase with time, it means that damage should increase as well. And displacement should increase as well. So actually, if we admit that force can also decrease, we could come back here along this branch. Unfortunately, as we are in force control, and this force control has this law, which is just force is increasing with time, unfortunately, we cannot come back because time goes on, so we cannot come back in time. But should we have a force such that the force can decrease even if time increases, then we could come back here and see the whole solution that we were observing in this previous case here, the displacement control. So also for the force control, we have an explicit scheme, which is you fix the force here, then you take damage at the previous time step, and you solve for the displacement. You plug the displacement here, and you compute the damage for the next time step, and then you repeat this iteratively. That's very easy. I go through these quite quickly, but then we have also Newton-Raphson. You have for sure heard this method in your courses on numerical analysis. Actually, this method should be adapted to the fact that damage is an only increasing function of time. So you just cannot solve a system of algebraic or whatever equations. You should solve a system of equations with not just boundary constraints, but also this irreversibility constraint over the damage. So you know the Newton-Raphson method just assesses the slope of a residual function, which here I have defined to be just the equilibrium condition, so Hooke's law in our case, normalized by the force. And using this linear approximation that exploits the knowledge about the slope of this residual, it computes an approximation of the zeros of the residuals. Of course, this method works only locally, as you may know, which means that you converge to the solution, to a given solution, only if you are in a sufficiently close neighborhood of that solution. And as you'll see, this method, because of this, is not very robust, because as the slope we deal with systems which are undergoing failure, so with systems who are, quite close to singular points, which means the stiffness matrices which we deal with are quite badly conditioned. These matrices are very close to zero, and inverting very close to zero matrices gives results which are sometimes hugely different, even when these matrices are quite the same. So you see, we move on a very unstable ground where very far solutions could be reached if not using a sufficiently stable or robust method. Then we have the fixed point. I will just skip this. By the way, the take-home message is just that explicit methods are really the ones which perform worst, while implicit methods, which is Newton fixed point methods, they are the ones which perform better on these kind of problems, because actually the explicit method has a lot of accumulation of errors which is going on. So you must refine a lot the step to get accurate solutions, but then refining a lot, you do a lot of steps, and in each of these steps you accumulate some error. This error grows indefinitely until you take unstable paths or you get non-accurate solutions. While implicit methods, for each step, do further steps so that you are sure that better accuracy is reached even with less steps. So here you see that here you see that indeed, well, what is that? This is the mean square error of in terms of displacements reached along a loading path. So here we are in force control because we are trying to assess the performances of the numerical methods that we have employed for this problem. So we need force control, because otherwise only the explicit method would be possible, because the system is completely determined in displacement control. So, well, you see that Newton method is the one that is performing the best, because in a force-controlled experiment where delta F, which is the loading step, has been fixed, we reach, well, the behavior, the log-log behavior, so that we have the logarithm of total computations on the abscissa and the logarithm of the mean square error on the ordinate is decreasing, so actually is going to 0, which means that we are converging, by the way. So we don't have any step dependency, at least for small steps. So the blue curve is as a slope, actually is quite linear, and this means that there is a well-defined asymptotic order of convergence of the method. So here you see that this curve has a slope which is much higher. So this error is going much faster to 0 than the other curves, which are related, which are obtained for different methods. So here the orange and the violet are both for the fixed point method, but one using a damage criterion for, say, as a convergence criterion for a given step, while here we use an energy criterion. The two of them are quite the same, because here we deal with a finite dimensional system, so all norms are equivalent in a finite dimensional system. And you see that the explicit method is the one that is performing worst, as I have anticipated to you before. Well, so you really need to increase a lot the number of computations to reach the same accuracy. Well, in numerical analysis, we call accuracy actually how close we are numerically to the analytical solution. Indeed, here I is the index of steps, so you have different force controlled steps. For each of these steps, you compute a displacement, and then you assess with this mean square error function how much you are far from the real solution. So you know which method is the best. Here we did the same for a different delta F, which is a lower false step. So again, here there are other comparisons, and here again we see this is a load displacement curve for the force control. And you see that basically all methods are, well, here we performed actually a cyclic loading process. So we increase the force up to a certain peak here, and then we decrease this force, we unloaded the system, following this linear path which is leading to the origin of this plot, because here we are dealing with damage, but we didn't introduce yet plasticity. So in this cyclic experiment, numerical experiment, you see that again, the exact solution is quite close to the green curve, which is for a very small delta F, while for larger delta F, which is 0.1, for example, the explicit method is working very poorly. So you see, this is the explicit method, and the explicit method is giving solutions that are varying a lot with the delta F, because the delta F controls how much steps you do for the explicit method. While for the other methods, which are all the implicit methods, they don't care about the size of the step, because then in between they do many other steps to ensure that the accuracy is always good. And so you see that no matter what is the tolerance that you give to the system, to the algorithm, you always reach a very good agreement between the analytical solution and the numerical one. So you have seen that our only, say, objective is, when we deal with the numerical analysis of these systems, we try to not using explicit method unless we cannot do otherwise, because you need very, very small steps, time steps, to reach good accuracy. And this in turn induces a lot of error accumulation. Okay, here we just study, I mean, these pictures were just meant to, as say, something that shows how we study if an algorithm is converging or not, even without knowing an analytical solution. So the question that we, as numericians, try to ask ourselves is, no matter where we converge, are we converging or not? So is our iteration law a contraction or not? Well, this is quite mathematically advanced, and I mean, only those of you who are interested, I will speak about this with those of you who are interested. Maybe you could ask some questions at the end about this. So here we have Newton method on a cyclic loading and unloading analysis. Well, actually, we are in force control. So you see here, we increase linearly until we get to a threshold. Here, softening starts. Then we should come back in principle because force is decreasing. So you see that for a cyclic loading, when force is decreasing, as I told you, in the analytical solutions, we would get, even in force control, we would get this softening here, this part here of the loading curve. And actually, Newton, even if we are just unloading, is converging to that branch of the solution. So here we have a kind of bifurcation. Both the unloading path, this linear unloading path, is a solution, as well as this other branch here is a solution, which is a further softening branch. But also all these unloading curves here are solutions once you reach, for example, this point here, and so on and so forth. So Newton is just, jumping between these solutions, which means that it is not capable of dealing with multiple solutions, or at least it is not able to continue following a given path, because convergence is really, say, controlled by where you are with respect to the solution to a possible solution of the problem. So you usually go with Newton to the closest solution you can get. Sometimes it jumps because of this. And well, so you see this behavior here. So at the end, let me just mention that we have an algorithm which is considered as the best algorithm we can use for this kind of problems. This is called the arc length control. So basically, we don't enforce neither the force nor the displacement. We just enforce the length of this curve. So this is equivalent to say that we fix a point along this curve. We select, we take a circle with a given radius, and then we say that we look for a point which is exactly intersecting with this circle, which is equivalent to say that we approximate this curve with a line, so that this line is actually the arc length of this curve. And then we look for this intersection here. Well, this is a very good algorithm, but unfortunately is incapable, say, as it is, of dealing with bifurcations, like in this case. So while Newton, for its own, say, drawbacks, can go beyond this point here, so it doesn't catch the unloading branch, but it catches this other branch in false control, you cannot do this with arc length. So while you get the correct solution here, when you have a linear unloading branch, which means a cyclic loading, you cannot unfortunately get this fatter softening here, which leads to collapse. So arc length method has to be improved to deal with this kind of problems. So to recap, we have a simple damaging spring, and even this spring is challenging numerical schemes. So it is a very good example. So is the simplest non-trivial example to assess and to get to know all these numerical methods. So Newton-Raphson is fast and can also sometimes go and go up beyond, say, some crucial points like limit points, and give, say, solutions which wouldn't be got otherwise, but jumps. Okay, it jumps. So it is not very stable. Arc length method doesn't jump, but is incapable of handling bifurcation. Explicit method is slow, as we have said, and fixed point is fast, but unfortunately cannot explore the full spectrum of solutions. So say that about say numerical methods, this is all. Now let's come to some applications. I will go very fast on this because I don't want you to really get the detail, but I want you just to get an idea about what we do. So here we model masonry structures as many bricks aligned over different rows, and each brick is considered as rigid, so it is not deforming at all, it's just rotating and displacing. And then we have elastic motor between these bricks. Well, actually this motor is elastic, but is also damaging. So after a given threshold, it starts to damage. So we call it theta n, the rotation, the angle, the anti-clockwise rotation angle of a given brick, which is labeled as n, and then un is the displacement of brick n. Well, so here we have some kinematical quantities that are defined for two adjacent bricks. I'm not going into the details of this. So what I just want to tell you is that if we know the rotation angle of all bricks, and in particular of two adjacent bricks, and if we know the displacement of the barycenters of these two adjacent bricks, then we can compute the relative displacement between this point here and this point here and this point here and this point here, which in the reference configuration lie in the same position. So actually what we do is we put here an extensional damaging spring, here an extensional damaging spring, so that here we take into account relative displacement between these two bricks, and also relative rotation, because one spring will compress and one spring will extend for a relative rotation of these two adjacent bricks. And then here we also consider two tangential springs. So we compute the relative displacement between this point here and this point here, and between this point here and this point here, using just representation formulas for rigid motions. Here you plug A and B, and you do the same everywhere else. And this is very easy, kinematically speaking. Then you define a deformation energy. So this is an elastic deformation energy, where these stiffnesses are, so you see here you have, this is the normal displacement, which is you take the displacement, the relative displacement between this point and this point here, and then you project this displacement along the normal, so this line here, to the contact surface, which is this, among the two bricks in the reference configuration. And then this displacement is just squared to get the deformation energy for this spring here. Again, if you have nu, you should put A and B to get the deformation energy of this spring or of this spring. While here you have the projection of the relative displacement onto the tangent to this contact surface in the reference configuration, which is just the vertical direction. So you project the relative displacement between this point and this point along the tangential vector, and then you square it, and if you multiply it by this factor, which is a rigidity, you get the deformation energy of tangential and normal springs acting between this point here and this point here, and between this point here and this point here. So we have 4 springs for each interaction among, let's say, for each couple of adjacent bricks. Of course, these stiffnesses, well, here we have a correction. So we have corrected the energy so that when the normal displacement for each of these nodes, for each of these couple of nodes, reaches a given threshold sigma, then this energy term diverges so that we take into account a sort of impenetrability condition. But this is a higher order correction. So of course, as I mentioned, the rigidities are damaging. And then here we have a correction, which is a surface correction. So of course, these rigidities are larger when there is a high contact surface, they are smaller when the contact surface is smaller. Damaging happens exponentially in tension. So here, you see? So we plug here this damage here, and happens much slower in compression. So we are dealing exactly with a motor, with motor as a material between bricks, which is quite realistic. We have, again, an exponential law for the damaging of tangential springs. And again, this factor here, which tells how much this exponential will go quickly to 0, is controlled by the stress state of the spring. When the spring is in compression, well, then this will be different than if we are in extension. So it's quite common that if you increase the pressure between two surfaces, then their sliding will be more difficult to achieve. Here, just an example, you displace this point here along this, this arrow, you apply here a rotation, theta, here all this row of bricks is fixed. And then you start the experiment, so you start pulling, and what you get is this. Here, no fracture is taken into consideration, which means that, well, let me come back here. You see, this guy here, this damage, will never reach 0. It will reach 0 only for an infinite relative displacement along the tangential direction. Also here, you will reach 0 only when, well, actually you will reach 1, sorry, you will reach 1. Also here you will reach 1, which means the exponential goes to 0, only when the projection along the normal to the contact surface in the reference configuration of the relative displacement between two adjacent vertices is going to infinite. This is not realistic, of course, because after a certain point, you reach complete fracture. So damage goes to 1 for a finite relative displacement. Well, here it is not taken into account. Well, you can see that here you have a rotation, here that induces a rotation of this brick. And you can see that whenever you have two adjacent grains or two adjacent rigid bodies, one is rotating in one direction, so say in anti-clockwise direction, then the next one should be rotating in the opposite direction, so in the clockwise direction. So this modeling is quite realistic in many respects. So, but as we don't deal with fracture, you see that along the horizontal direction we have kind of softening, but don't reach fracture. And the same along the vertical direction. So this is just the load displacement curve along the horizontal and vertical direction. Well, here now we introduce fracture, which means after damage reaches a given threshold, then that interaction is cancelled. And when all the interactions among two adjacent bricks are broken, then you have really fracture of the mortar there, which is denoted by a red line. So here you see that we see the results without that the fracture is highlighted. Now very soon we should see fracture with, yes, fracture. So you see that here fracture has occurred. Here fracture is occurring, but still it's not reached. Here fracture has occurred completely. And well, if we look at the force displacement diagram, here we can see an initial softening. Then as before, we see a stationary point, which is called the limit point. And then the force is decreasing until it reaches 0 along the horizontal direction. While along the vertical direction, a very nice thing is happening. But actually we have the same behavior, except that we reach a plateau because there are still some of them which are resisting, right? There are still some of them which are resisting, but then also then they get fractured, and so we see that this last attempt that the material has done to resist, because the load has been transferred to other interactions, fails until we indeed eventually get to 0 force. So very briefly, very quickly, we have also continuous models of retrofracture. Very fast, this is based on continuum mechanics. So here we have all the formulas we have dealt with in the discrete case, very simple, with a few degrees of freedom. We have this in an infinite dimensional setting, so in a continuum setting. Well, and we get fractures. We get fractures which are propagating along the material, quite realistic fracture for isotropic, anisotropic materials, fracture for materials with a complex shape or with a complex loading state. You see here we have a hole and a fracture. Here we have an extension of this specimen along the vertical direction, and the fracture is initiated here at the crack, at the notch. There's an initial notch, and then the crack is attracted by this zone, which is less rigid than the other parts of the material. We have the effect of Poisson's ratio, which governs how quickly the fracture deviates, both here and here. Then we have homogenization of, so we have micromechanical approaches, which is continuum approaches, which are based on some modeling at the micro scale. And this modeling at the micro scale is not just taking into account damage, as we have seen for the masonry, but we have also plastic interactions. Well, you can have loading and unloading cycles with plasticity. Of course, for each direction, for each point, you have a given damage. So you have a lot of, you have not just as here, these fields, these say contour plots for the damage, but you have that for each point, you have a polar plot for damage, be it tangential or normal damage, because for each point, you have two adjacent particles along each direction, which are interacting, like in the masonry. This is nothing but the homogenization. So we have transferred to the continuum the description of the masonry that you have seen before. And of course, as damage is different, if we consider different directions for each point, then this induces an anisotropy, because stiffnesses change with the direction. So basically, let me say that what is important maybe for you is to know what we would do together in the future. So we would analyze relevant cases for which there are analytical and numerical results in the existing literature, using the masonry model that I presented before, so that we can check whether it is consistent or it is better or worse with respect to previous literature, or if it can describe better some real experiment. We would like to use this masonry model to identify a Coursera continuum. So we would like to use micromechanical homogenization to homogenize the masonry, including plasticity and rotation of bricks, which has not been taken into account up to now. As I said before, introduce plastification of the elastic interactions among the bricks in the masonry, introduce more complex elastic constitutive laws, study the stability of the different configurations using these models, study out-of-plane phenomena, add inertial effects, which means kinetic energy, to study dynamic problems like earthquakes, and then finally apply the methods that we have developed to more standard approaches like the discrete element models. So I thank you for the attention, for having resisted up to now. And please, if you think to be interested in finite element method, in numerical analysis, continuum mechanics, civil engineering applications of all what I have presented so far, please take into serious account the possibility of doing your thesis within our investigation group at the Instituto de Investigación Científica of the University of Lima. And we'll be very happy to welcome you into our group, and also exchanges with Italy are forecast. So thanks for the attention.
Emilio, muchas gracias. Como lo acaba de mencionar, para los estudiantes y colegas que estén interesados en las temáticas que ha expuesto Emilio, dentro del Instituto de Investigación estamos desarrollando un proyecto afín a lo que él ha comentado. Si bien es cierto, se ha hecho una exposición física, matemática del comportamiento de la modelización de estos fenómenos, es lo que se necesita para poder entender después la simulación, ¿no? La simulación pasa por un modelo que necesita de diversos conocimientos que él ha venido comentando a lo largo de la presentación, que muchos de los alumnos vienen recibiendo en los diferentes cursos que están llevando hasta el 8º ciclo aproximadamente. Entonces, si hubiese alguna consulta de parte de ustedes, vemos que no, bueno, en la chat no se presenta, pero de todos modos nos pueden siempre escribir. Les voy a dejar el correo también, o el mío, o el del profesor Jaime Espinosa, a través del cual ustedes se puedan comunicar. Y bueno, tenemos también la disposición para con los alumnos poder formar un grupo de investigación, más que todo dedicado para la parte de simulación. Próximamente vamos a realizar de los cursos de capacitación la modalidad de webinar en el uso del software Console Multiphysics. Bueno, acá les estoy dejando el correo. Si tuviesen algún interés en comunicarse con nosotros. Muchísimas gracias otra vez por vuestra presencia, vuestro interés en el seminario, y que se le agradece a todos, también al profesor Emilio por el tiempo que nos ha dedicado. Nos estamos viendo, a la próxima.